Welcome to lecture 19, where we discuss the function sequence criterion, uh, which can be summarized as follows. The limit of a function can be used to compute the limit of a sequence. In other words, we are given a sequence, we need to evaluate the limit of the sequence, we don't know how to do that, then we can rely on a limit of a function of which we know the limit. So to give you the idea, which is basically the opposite of the sequence function criterion, okay, we are now in a situation where we need to evaluate the limits as n goes to infinity of some sequence. For example, let's take this sequence n times sine of 1 over n, and we immediately recognize that this is undetermined form because it's going to be infinite times 0. We can rewrite, as a first step, we can rewrite this limit as a limit as n goes to infinity of sine of 1 over n divided by 1 over n. And now, if we set 1 over n, which is a real number, equal to a new variable y, we see that when n goes to infinity, y goes to 0 plus. So this limit is now the limit as y goes to 0 plus of sine of y divided by y, which we know is equal to 1. In fact, this is one of the fundamental limits that we have introduced in lecture 17. So that's the idea. We don't know how to solve the limit of a sequence. We will rely on a limit of a function. Now, what is the theorem behind this criterion? So this is the theorem. Let f be a function defined in some subset D that takes value in R, and let a n be a sequence of real numbers. Now, if an, the real sequence, tends to x naught, which is an element of the extended real line, so can be finite or infinite. If for every natural number n, or at least definitively, we have that this sequence an belongs to the domain of definition of the function d, except the point x naught. If the limit of f of x as x goes to x naught is equal to L, which is again into the extended real line, then we can conclude that the limit of f evaluated now at the point of the sequence, which is an, for n that goes to infinity, this limit is exactly the same L. Okay, so basically the idea is this one, that we know something about a function. Okay, we know that the limit of f of x as x goes to x naught is equal to L. We want to use this to solve the limit of a sequence. So basically, by just replacing x with an and knowing that when x goes to x0 n goes to infinity, we can just say that the limit of the function evaluated now not in x but just at the points of the sequence an as n goes to infinity is equal to L. Okay, now I think it's very useful to look at the proof of this theorem. So the proof is quite straightforward. but it is useful to understand what is happening, why we can use the function to solve the limit of a sequence. Now we have many possible cases here, because x naught can be a real number, x naught can be plus infinity, x naught can be minus infinity. Okay, so we have these three possibilities, because the hypothesis one was just saying that this x naught is in the extended real line, so it can be finite or can be infinite. And for each of these cases we have three possible situations, because L also belongs to the extended real line, so it can be a real number, it can be plus infinity, it can be minus infinity, and same thing for the other cases. So in total we have 9 cases, but the proof is quite similar, so we will pick just one case. For example, we will pick the situation where x naught is real and L is real. So we wish to prove, so let's restate the theorem for this specific case. So we have function f defined in D with values in R, an a real sequence, and we have hypothesis 1 now is that an, the real sequence, converges to a real number x naught that now belongs to R. Second, for every natural number, or at least definitively, this sequence an belongs to the domain D except the point x naught. Third condition is that the limit of f of x as x goes to x naught is equal to L, and we want to prove that the limit of f evaluated at the sequence an as n goes to infinity is equal to L. Now proving this is just like saying that for every epsilon larger than 0, f of an minus L in absolute value is less than or equal to epsilon definitively. But by the condition 3, we know that limit of f of x when x goes to x naught is equal to L, which implies that for every epsilon larger than 0 there exists a delta larger than 0, such that if x belongs to x0 minus delta, x0 plus delta, intersection D without x naught, if this happens, then f of x minus L in absolute value is less than or equal to epsilon. This is just the definition of limit applied to this limit here, right? So it suffices to prove that an will belong to x naught minus delta, x naught plus delta, intersection D, except the point x naught definitively, because if this happens, f evaluated at an will just satisfy the previous condition. But this is true because, well, an will belong to this interval definitively by the condition 1, because in the condition 1 we know that an tends to x naught, which implies that definitively it must be that this is true by condition 1. But we also know by condition 2 that an will definitely belong to D except the point x naught. So this is true by condition 2. So this finally proves the theorem. So we know that the condition is satisfied. As a final observation, we can say that all the changes of variable in the limits can be proved with the previous theorem. In fact, what we have just proved is indeed a change of variable. Okay, instead of using x as the original variable, we are just replacing x with a sequence an, but we could possibly do the same with another real variable, and the theorem still remains valid. Okay, now let's introduce a new technique which is very powerful for the computation of limits, and it is the technique of exponential transformation. And we will introduce these both for sequences and for function. Okay, so this technique can be applied to limits of the type an sequence raised to another sequence bn, or also when we have a function f of x raised to a new function g of x. So what's the idea behind this? Well, the idea is the following. Let me give the idea in green. Okay, so the idea is the following, that if we have an raised to the bn, we can also rewrite this as e raised to what? Raised to the logarithm of an raised to the bn, which by the properties of the logarithm is just like writing e to the bn times the logarithm of an. The same story goes for the function. If we have a function f of x raised to g of x, we can rewrite this as e raised to the logarithm of f of x to the g of x, and again this becomes e to g of x times the logarithm of f of x. Okay, so let's see how this works in context. Let's take this example. Okay, let's suppose that we want to prove one of the fundamental limits that was left in the list. Limit as x goes to 0 of a to the x minus 1 divided by x, and we immediately recognize that this is one of the undetermined forms, because when x goes to 0, of course the denominator becomes 0, but also the numerator becomes 0. So 0 over 0 is one of the undetermined forms. Okay, so first step is to replace a of x by the transformation to the exponential. So I will rewrite this as limit as x goes to infinity, to 0, sorry, of, instead of writing a to the x, I will write this as e to the x logarithm of x minus 1. And then instead of having x, I would prefer to have x logarithm of x and then multiply by logarithm of x. Okay, you see that clearly the right hand side is just like the left hand side. I have just multiplied and divided by logarithm of x. But now we see that this first limit with the simple change of variable y equal to x log x. Sorry, there was a mistake. This is clearly logarithm of a, not x. This is logarithm of a, and also this is logarithm of a and logarithm of a. Okay, now if we make this change of variable and we say that y is equal to x logarithm of a, clearly we see that when x goes to 0, we have that also x logarithm of a goes to 0, which is to say that y goes to 0. But this limit, we know this already, and we know that this is just equal to 1. So this finally proves that this limit is just equal to the logarithm of a. Okay? Let's give another example of application of this transformation to the exponential. Another example is the following. Let's say we want to evaluate the limit as n goes to infinity of n times the nth root of 24 minus 1. Okay? And what is the form that we get if we just replace n that goes to infinity? We have infinity and we have 0. So once again we have an undetermined form. So we need to find another way to compute this limit, right? And we can rewrite this as limit as n goes to infinity. This n can be taken to the denominator and will become 1 over n. Okay, and instead the numerator can be reformulated as 24 raised to the 1 over n minus 1. Okay, so this is just the same. And now if we put, okay, if we put x equal to 1 over n, okay, we can do this because 1 over n is a real variable. We see that when n goes to infinity, x goes to 0 plus. So the limit is now limit in the new variable x that goes to 0 plus of 24 raised to the x minus 1 divided by x. But we have just proved in the previous example that this is nothing else than an example of this limit with a being 24. So we can just write now that this final limit is simply the logarithm of 24. Okay? Okay, so the conclusion is this. So what's the idea behind this transformation? Is that limits with variable base and variable exponent, because this is where we are, right? So we are talking about sequences like this where the base is a sequence and the exponent is a sequence, or limits like this where the base is a function and also the exponent is a function. So limits where the variable is a base and with the variable exponent, they just become limits of products. So this is the fundamental idea behind the transformation to the exponential. Okay, now that we have this other tool, we are finally ready to introduce the algebraic theorem of the exponential. And we'll introduce this just for sequences. And then we'll see if we can just reuse this result for function, or we just reformulate this for functions. The theorem says that if an is a sequence that tends to L1 that belongs to the extended real line, and Bn is a sequence that tends to L2, another limit in the extended real line, then an raised to the Bn will simply tend to L1 raised to the L2. Now this is valid in general, except for undeterminate forms like 1 raised to the plus minus infinity, or 0 raised to the 0, or plus infinity raised to the 0. Okay, for which in fact for these cases it happens the sequence Bn logarithm of an, which is just the result of the transformation to the exponential, is undeterminate. And let me prove this. Okay, so I just want to prove that if you have a sequence an bn, and if you just try to evaluate the limit as n goes to infinity, you basically have a form of the type 1, because an tends to 1 and bn tends to plus or minus infinity. You will basically in the position of having this form, 1 raised to the plus or minus infinity, okay, which is the first one that we were considering. I want to prove now that this limit is not 1, okay, but it is one of the undetermined form. In fact, if we just replace, so this is basically what happens. Okay, let me rewrite this clearly. This is what happens when an tends to 1 and bn tends to plus or minus infinity. Then what I get is that I basically have this becomes the form 1 raised to the plus or minus infinity. But if I do the transformation with the exponential, then I know that I will end up evaluating bn times logarithm of an, but Bn, this will become plus or minus infinity times the logarithm of 1, which is once again one of the fundamental cases of undetermined form, infinity times 0. Let's see what happens if, when evaluating an to the bn, it happens that an goes to 0 and bn goes to 0. Well, then I will be now evaluating a form 0 raised to the 0, which by the same exponential transformation implies that you will have 0 times the logarithm of 0. But this is 0 times minus infinity, so another undetermined form. Finally, if you have an to the bn and an goes to infinity, let's say to plus infinity, and bn goes to 0, then you have the form infinity raised to the 0, right? Plus infinity raised to the 0. And by the same exponential transformation, you are led to 0 times the logarithm of plus infinity, which is once again 0 times plus infinity. So we proved that in these three cases, when evaluating a sequence raised to the other sequence, and we try to get the limit for n that goes to infinity, we end up in one of these three cases that correspond to undetermined form. So in this case, of course, the algebraic theorem doesn't work. Okay, we cannot just use this result. So basically, this result is not valid anymore. Let's give the proof for this theorem. What is the proof? Well, the proof is just a very straightforward application of the transformation to the exponential, because if we have an to the bn, we can rewrite this as e to the logarithm of an raised to the bn, which is equal to e to the bn times the logarithm of an. Okay, and now, because we know that the logarithm is continuous, then we can just say that this will tend to e raised to the logarithm. We can rewrite this. Let me do this. Let me rewrite this as e to the logarithm of an, all this raised to the bn. Okay, and now, because of the continuity, logarithm is continuous, then we can say that this will tend to e to the logarithm of L1, all raised to the L2, which is nothing else than L1 raised to the L2. And this finally proves the theorem. To appreciate the power of this theorem, let's apply this to a number of examples. Okay, let's start with this example 3. Let's say that we need to evaluate the limit as n goes to infinity of n, and this is multiplied by the nth root of n minus 1. Okay, and you remember that I will just remind you that we proved that the nth root, the nth root of n will tend to 1, and we did this by just applying the ratio root criterion. I'll just remind you how we did this. We just have that an is simply n in this case. So the ratio root criterion says that if we find an plus 1 divided by an, and we'll see what is the limit of this, this is exactly the limit of the nth root of n. But the an plus 1 divided by an, this is nothing else than n plus 1 divided by n, which we know tends to 1. And this therefore implies that the nth root of n will tend to 1. Okay, so this proves that if we just replace this, what is the form that we have? Well, n goes to infinity, and instead what we have in parentheses is just 0. So we have another again, an undetermined form. So how can we proceed to solve this? We can rewrite this as the limit as n goes to infinity of this n goes to the denominator as 1 over n. Then we have n to the 1 over n minus 1 at the numerator, right? And this is by reapplying the transformation to the exponential. We have 1 over n, but let's first transform n to the 1 over n. So we can rewrite this as e to the 1 over n logarithm of n minus 1. So we would like to have at the denominator 1 over n logarithm of n, which can be simply obtained by multiplying and divide by logarithm of n here. Okay, so at this point what we can say is that the first term, this term, if we set y equal to logarithm of n divided by n, clearly we see that if we have n that goes to infinity, we have that y goes to 0 just because the power wins over the logarithm. So this proves that this limit is once again 1 because y tends to 0. So the conclusion we have now is that this limit is simply logarithm of n, which of course will diverge to plus infinity as n goes to plus infinity. Another example. Example 4. Let's consider now the limit of a function. Limit as x goes to 0 of cosine of x raised to the 1 over tangent square of x. This is an undetermined form. Cosine of x will tend to 1 when x goes to 0, and instead 1 over tangent square of x will go to plus infinity. So this is one of the undetermined form. Now let's apply the transformation to the exponential. This becomes limit as x goes to 0 of e to the logarithm of what? Well, the logarithm of cosine of x raised to the 1 over tangent square of x, which is equal to the limit as x goes to 0 of e raised to the 1 over tangent square of x times the logarithm of cosine of x. So we are led now just to evaluate the limit as x goes to 0 just of the exponent, which is the only part that changes with x. So we have logarithm of cosine of x divided by tangent square of x. But now we use the usual trick of adding and subtracting 1, and we have 1 plus cosine of x minus 1, okay? And now we can also rewrite this as limit as x tends to 0 of, we have logarithm of 1 plus cosine of x minus 1 at the numerator. Then we need to have another cosine of x minus 1, because we know that when x goes to 0, cosine of x minus 1 goes to 0, and this is one of the fundamental limits that we know. However, we need also to have cosine of x minus 1 is just multiplying and dividing by the same term. And we know that this will offer another fundamental limits if it is divided by x squared. So we have to have another x squared divided by tangent square of x here. And let's see one by one each of the fundamental limits, what they give us. Well, these limits, if we set y equal to cosine of x minus 1, we know that this, of course, y will tend to 0, and this will offer the fundamental limits which tends to 1. And this is basically is another fundamental limits with the inverted sign, so this will tend to minus 1 over 2, and instead this is just the inverse of one of the fundamental limits, so we know that this is going to be 1. So this limit is minus 1 over half, and therefore we can conclude that the limit as x goes to 0, remember the original limit was cosine of x raised to the 1 over tangent square of x, cosine of x raised to the 1 over tangent square of x, that by the transformation to the exponential became limit x goes to 0 of e to the logarithm of cosine of x, logarithm of cosine of x divided by tangent square of x, which we prove. Now we have just proved that this exponent will tend to minus 1 over 2, so this limit is simply e to the minus 1 over 2, or if you like, 1 over the square root of e. Okay? Good. Example 5. Limit as x goes to 0 plus of logarithm of sine of x divided by logarithm of x. What is the undetermined form that we have here? Well, we basically have a fraction. When x goes to 0, logarithm goes to minus infinity. But when x goes to 0, also sine of x goes to 0 plus, and we have another minus infinity. So in this case we have infinity over infinity. Well, in this case we can resolve this undetermined form by just rewriting the logarithm of sine of x divided by logarithm of x. We recognize that sine of x can give rise to a new fundamental limits, so we can write logarithm of sine of x divided by x and then multiply by x, and then we have logarithm of x, right? And we can now apply the properties of the logarithm at the numerator, and we get logarithm of sine of x divided by x plus the logarithm of x, all this divided by the logarithm of x. And we immediately recognize that this, when x goes to 0, this is one of the fundamental limits, this will tend to 1. Okay, so we can rewrite this as, by just splitting the fraction into 2, we have logarithm of sine of x divided by x divided by the logarithm of x plus 1. Okay, and now we see that this tends to 1. So this implies that this entire limit, this entire numerator tends to logarithm of 1. So this is basically 0. And instead, the logarithm of x, when x goes to 0 plus, this will go to minus infinity. So that implies that the first term will go to 0. And so we can conclude that this limit is 1. A similar example is this one. Let's take the limit as x goes to 0 plus of this fraction. We have logarithm of sine of x squared and logarithm of arc tangent of x. We can play a little bit with the arguments of the logarithm. First of all, we recognize that this is another undetermined form, because when x goes to 0 plus, sine of x squared goes to 0, so we have minus infinity at the top, and the same thing happens at the bottom. So we have once again an undetermined form of the type infinity over infinity. But we can rewrite this as the limit as x goes to 0 plus, just playing with the arguments of the logarithm. We can rewrite the argument as sine of x squared divided by x squared times x squared, and at the denominator we can write logarithm of arc tangent of x divided by x times x. And we see that we have two fundamental limits which we can use. So let's apply now the properties of the logarithms, and we get at the numerator we have the logarithm of sine of x divided by x, all this to the square, plus 2 times logarithm of x. And then we have logarithm of arc tangent of x divided by x plus logarithm of x. Okay, let me make some space here between these two. Now, let's see what the fundamental limits will provide, because we know that this limit will tend to 1 as x goes to infinity, which implies that this entire limit will go to 0. The same way, we see that this entire limit will go to 0. As a result, this limit is simply equal to 2. Let's consider now this other example. So, example 6, limit as x goes to 0 of e to the sine of x minus cosine of x divided by the logarithm of 1 plus tangent of x. And let's check first what happens when we just replace x that goes to 0. We clearly have 0 at the numerator because we have 1 minus 1, and at denominator we have another 0. So we have another undetermined form, okay? And because clearly when x goes to 0, tangent of x becomes 0, so we're left with the logarithm of 1, which is 0 again. Now, we can try to extract some fundamental limits from this expression. So let's rewrite this as limit as x goes to 0 of, well, because we have e to the sine of x, we might think of replicating that limit e to the x minus 1 divided by x. So we can rewrite this as e to the sine of x minus 1 plus 1 minus cosine of x. And then, well, as a first step, let's leave the denominator as it is, 1 plus tangent of x. Okay, but now we can do this. We can rewrite as limit as x goes to 0. At the numerator, we can rewrite, make some space here, we can rewrite that e to the sine of x minus 1, we can divide by sine of x and multiply by sine of x, but then we need another x here and another x here. So basically this is what makes these first two elements, okay? These are just now reformulated in terms of this multiplication of three terms. And then we'll go to the other part, which is basically this part here. Well, this part here will become plus 1 minus cosine of x divided by x squared, and then we multiply by x squared. Okay, and so this is the green part, and we see that, okay, so this is the green part. Now let's see what happens at the denominator then. Also the denominator, we need to do some transformation. We have the logarithm of 1 plus tangent of x, but because tangent of x goes to 0 when x goes to 0, we can think of dividing this by tangent of x and multiplying by tangent of x. This is not enough. We again divide by x and multiply by x. Okay, so this is exactly the same limit as before, but where we have extracted some fundamental limits. And in fact, let's now one by one see what happens with all these limits. The first thing that we realize is that we can easily simplify this x, and this square, which just leaves an x on the second term of the numerator. Then we see that, let's say this limit, when x goes to 0, this will tend to minus 1 over 2, right? And instead, this limit will tend to just 1. This will tend to 1. And this also, this limit as well will tend to 1. So, well, let's go now to the denominator, and we see that this limit once again tend to 1, one of the fundamental limits. The same happens for this other limit. So finally we are led to the limit as x goes to 0 of, we have just 1, because the first term at the denominator is just 1, minus 1/2 times x divided by 1. But of course, this is a continuous function. When x goes to 0, this limit is simply 1. Final example, example 7. Let's consider the limit as n goes to infinity. We are now taking the limit of a sequence, and the sequence is the nth root of 7 minus the cosine of 1 over n, all divided by sine of 1 over n. And if we look at this limit, we recognize that this is another undetermined form, because the denominator will go to 0 just like the numerator, so this is 0 over 0. So we need to devise some alternative procedure, and we can transform this. This is a sequence. We can use the function sequence criteria, namely using the limit of a function to help the calculation of a limit of a sequence. And let me first rewrite this as 7 to the 1 over n minus the cosine of 1 over n divided by the sine of 1 over n. And by just setting x equal to 1 over n, we see that when n goes to infinity, x will tend to 0 plus, right? So this is just equal to the limit as x goes to 0 plus of 7 to the x minus cosine of x divided by sine of x. But we know how to solve this limit. We have done this already. So we can rewrite this as limit as x goes to 0 plus of, let's do a little bit of transformation. Well, the denominator will become sine of x divided by x times x. At the numerator, subtracting and adding 1, we have sine 7 to the x minus 1, which we would like to divide by x and multiply by x, and then we have 1 minus cosine of x divided by x squared, and then we multiply once again by x, right? And now we see that we recognize some fundamental limits, because this will tend to 1, this will tend to 1 over 2. We can simplify the x's, and we see that this will tend to the logarithm of 7. So this limit is now simply the limit as x goes to 0 plus of basically the denominator is 1, it's just a constant, so we have the logarithm of 7 plus 1/2 times x. But when x goes to 0, this is a continuous function, so we finally get logarithm of 7.